Good morning, Physics 20. I hope you guys are doing well today. So what we're going to be looking at is we're going to be looking at inclined forces today. So do you guys like the pun? It's a cute angle. Yeah, pretty awesome. Love that one. So, ladies and gentlemen, we are going to be using acute angles today when we're going to be looking at our inclined forces. So we're going to be looking at when you're either pushing at an object or pulling at an object at an angle to the horizontal. So imagine pulling at a toboggan. When you're dragging a little kid on a toboggan or pulling a kid in a wagon, you are going to be applying a force on the X and on the Y as well. Excuse me. Okay. Let's turn that off. Okay. So when we're going to be applying forces on the X and on the Y, we are not only going to be contributing to the acceleration along the X, we are going to be contributing to our normal force. We're going to be changing our normal force. So those are going to be our two big focuses for today. And we also, as always, are going to have a field trip as well. Okay. So let's grab, we're already on the pen here. So we're just going to scroll down. We're going to start looking at our next piece. Now, can I actually scroll over a bit? Yeah, there we go. That's okay. All right. So, ladies and gentlemen, when we're going to be this is what we got here for your notes. So please underline that we're going to be looking at both vertical and horizontal forces acting on an object at the same time. Now, once again, we always keep all of our vectors on the X and Y separate. So we are going to be having to separate our F net equations into our F net on the X and our F net on the Y when we're going to be looking at our calculations. So the best thing we can do here is jump right in. Oh yeah. So, ladies and gentlemen, what you could also do is if you would like to watch the field trip prior to continuing on with this point, I'll be explaining in the field trip today while I push around my desk chair the differences between forces acting on the X and on the Y and why we have to break that apart. So you're welcome to pause the video and then go look at the field trip and then come back here for the calculations. All right, so ladies and gentlemen, are you guys ready to do the math? All right. So let's look at the question. So what we've got is a father pulls his children in a wagon along a flat road heading east. The kids in the wagon have a mass of 65 kilograms, and if the father pulls the wagon with a force of 82.3 newtons at 53 degrees relative to the road, and there's a force of friction of 26.5 newtons, what is the acceleration with the wagon with the kids on it? All right. So, ladies and gentlemen, let's begin. The same as always, what we always do is we're going to draw ourselves a free body diagram. So, here's the ground, and here is our wagon. And our velocity is going to be going on the east, towards the east. And as always, we are going to have a force of friction opposing motion. We have a normal force, which is the force of the ground pushing up on the object. And we have our force of gravity pulling down on the object. So all of those are the same. None of that is new. What we do have, though, is our force that is going to be applied is now going to be at an angle. So the father is pulling on the wagon, but he's applying that force upwards at an angle. So the 82.3 newtons is now here at this angle. Okay. The angle is our 53.9 newtons. I'm just going to extend this arrow a little bit, so then that way it'll be easier for us to make our triangle a little bit later. There you go. So ladies and gentlemen, let's think about this for a moment. Notice how this 82 newtons here, that is not being applied just on the x anymore. That has an x and a y component. And because the kids on the wagon are not being accelerated up through the air or down through the ground, our acceleration is going to be on the x only. Now, the force that is on the y component of this force is not contributing to the acceleration. We will look at more in our next question on how it does impact our force of friction, but that's next question. This question, we are just going to be focusing on the y, or on the x, excuse me. So we have to break this vector, ladies and gentlemen, into its x and y components. This is our force applied on the x component of that force applied. On the y here, we have our force applied on the y, and this is our force applied overall. So be very cautious, ladies and gentlemen, that we are paying close attention to labeling these guys as our force applied x, force applied y. Do not use just the plain old force applied on your calculations directly, because this force applied here, this guy right here, has x and y components. This is the only part of the force that is contributing to the acceleration. So let's figure out what that is. So our force applied on the x is our hypotenuse. Okay? We are going to be using trig in order to determine what that force applied is. So am I going to be using cosine, sine, or tangent? Cosine, you are correct. Now, the reason why it's cosine is because our force applied on the x is adjacent to this angle. So that's what we're going to be looking for. So our cosine of 53.9 degrees is going to be, I forgot to write my equal sign, is going to be equal to our force applied x divided by our standard force applied. Okay, so we're going to and that is the 82.3. So we're going to rearrange this equation, and we're going to multiply both sides by that force applied. So we are going to have our 82.3 newtons times our cosine of 53.9, and that is going to equal our force applied on the x. Okay. So once you put that into your calculator, making sure your calculator's in degrees, as you are going to get a lovely value of 48.4908 newtons. Once again, on the x. That is the force that is going to be applied on the x. That's the force that's contributing to that acceleration. Okay, so I'm going to scroll down a bit here. There. Okay, so we're going to need to, as we've done previously, make an F net equation, except this time it's going to be on the x alone. So let's think carefully. Our force applied x is going to be contributing to our F net, and the force that's going to be impeding our motion is going to be the force of friction. Well, that value has been given to you, so we don't need to calculate that. Now let's think about F net. Remember, ladies and gentlemen, that F net is equal to ma. Okay, we have the mass. Okay, we have the mass of 65.0 kilograms, and we're trying to find acceleration. So I am going to divide out that mass And my acceleration is going to equal my force applied minus the force of friction divided by my mass. So I'm going to put my numbers into my equation here. So my acceleration is going to give me my force applied on the x using all numbers from your calculator, all of those digits, and you're going to subtract that from your force of friction, which is going to be your 26.5 newtons. And we divide that by your 65 kilograms. And that's going to give us the acceleration, once it's in your calculator and done correctly in your calculator, 0.3383 ... meters per second squared. So now, ladies and gentlemen, I want sig digs, I want directions, I want units. So we have our acceleration. And when we come back to the question, I want 3 sig digs. So that means it's going to be 0.338 meters per second squared. And we're also going to need a direction here because the motion is going to, father's pulling the kids on a wagon east, and motion's going to be east. All right. So what do you think? Not too shabby. So the big trick with these, ladies and gentlemen, is to really, really pay very close attention to where which force is actually contributing to which motion, and making sure you break these forces on angles into their x and y components. Okay. Are you guys ready for question 2? Oh, yeah. All right. So let's scroll down. Okay. Now let's see if I can I possibly drag this thing over? No. Let's try that. So let's see if I can zoom in a bit more, this might be a little bit easier. There we go. Okay. All right. So ladies and gentlemen, this is going to be a rather tricky question. There's a lot of things that are going to be happening here, so I'm going to need you guys to pay some close attention here. All right, so this question, I have now given you mu. You are going to need to calculate your force of friction, so we're going to have a whole nother component of things that we're going to be keeping track of. So we'll take our time with this one, and I really want you guys to pay close attention. Okay. So 12.7 box is being pulled east along a horizontal surface with a force of 60 newtons acting at an angle of 42 degrees. If mu is 0.23, what is the acceleration of the box? Okay, so same as always, ladies and gentlemen, we are going to draw our free body diagram. Here's our box. And it is being pulled. Now, that's another key term to look at. If we're pulling it, we are going to be pulling upwards like that. Okay. We have our force of friction acting in opposition to our motion. Our motion is going to be going to the east. We have our normal force acting upwards. And we have our force of gravity acting downwards. So, ladies and gentlemen, this is where it's going to become even more tricky, because we're going to be needing both force applied on the x and force applied on the y for different purposes. Okay, so we're going to label this as our 42 degrees. And this guy here is going to be our force applied on the x. And this is going to be our force applied on the y. Okay, so that part is the same as the previous question. So let us begin by writing out our FNet diagram and determining all the components that we're going to need. All right, our FNet diagram, FNet equation. Now, keep in mind, my acceleration is going to be on the X. This box is not flinging its way up through the air or sinking its way through the floor. It is accelerating on the X. So that is where we need our acceleration to be. So our F net on the X is going to equal my force applied X minus my force of friction. So far, it is the same. So far, everything is the same as our previous question. We're going to use cosine to find our force applied X, so that's there. We have our F net equals ma, so we still have that. The difference here now with this question compared to the last one is this force of friction right here. I have not given you force of friction. I have given you mu. I've given you the coefficient of friction. So let's break this down a little bit more here. So ma on the X is going to equal my force applied X minus my normal force times mu. Remembering that your friction, your force of friction is mu Fn. Okay, I just wrote them backwards there for no particular reason. So ladies and gentlemen, I need to find my Fn. That is where our force applied on the Y is going to come in. So let's do the easy part first, and let's find our force applied on the X. Okay, so I'm going to use cosine, same again here, because this here, my force applied, my overall force applied is my hypotenuse, and what I'm trying to find is adjacent, so that's going to be cosine. So my cosine of 42 is going to equal my force applied X divided by my overall force applied, and which is going to then give us, I'm going to multiply out that force applied on both sides there. So my force applied of 60 newtons, that's a 60, times my cosine of 42 is going to equal my force applied X. And once you put that into the calculator, you are going to get the wonderful value of 44.5886 ... newtons. Okay. So, ladies and gentlemen, we now have that value. When we are going to go build our equation, we are going to be putting this guy right in here. Okay, this is where the tricky part's going to come in. We are now going to need to get our force normal, our normal force. And we are going to need our force applied on the Y for that. So while we're at it, let's just calculate that number, and then I will show you why we're going to need it. Okay, now for force applied on the Y, okay, the same principle as our as the previous one, we're going to use trig in order to find the force applied on the Y, except we're now not going to use cosine, we're going to use sine. Excellent. Force applied on the Y is opposite to this guy here. So that means we're going to use sine. So our sine of 42 degrees is going to equal our force applied on the Y, and we're going to be dividing that by the overall force applied. So once we rearrange this, and you're going to have your 60 of sine 42 is going to equal our force applied on the Y. Okay. Or as my last year's physics 20s like to call it, FAPI. That's how it's spelled out there. Good. All right. So your force applied on the Y is your 40.1478 ... newtons. Okay, so leave all those values in your calculator. And we're back, ladies and gentlemen. After technological difficulties, my modus operandi, tech doesn't work. Okay. So we're back, and everything we've done so far has deleted itself. Thank you, technology. So instead of rewriting everything, I'm just going to record some of the key values that we're going to need. Then you can always go back in the video to see how we got them. Okay, so your force applied is on the X. We calculated earlier in the video to be our 44.5886. We calculated earlier in the video to be our force applied on the Y to be 40.1478 newtons. And the other key piece that we are going to be needing is we're going to be needing our F net equation on the X, which is our force applied X minus our force of friction. And I'm going to quickly redraw our free body diagram here. And we're getting there. Okay, we're back. At least workable amount of info here. So, ladies and gentlemen, when we re-break this down, we're going to be looking at our mass times our acceleration. Excuse me. So we have our force applied X, which we have already calculated. And we're going to be then subtracting this from our mu Fn, which is our equation for calculating the force of friction. So we now have we have mu that's applied to you. We have mass, we have force applied X, but we don't have Fn. Now, remember how in the previous lessons we've done a lot of our F net equations on the Y in order to get our Fn. This is the most common mistake that I see in this topic. Watch carefully here. Okay, this is where I see the most mistakes. We need to make, in order to get this guy here, we are going to need to make an F net equation on the Y. Now, we no longer just have Fg and normal force acting here. We have force applied Y. Because you're pulling upwards on this object, you're pulling it up, we're reducing the force that is actually being applied by the ground. Okay, so that means our normal force is going to be less than our Fg. Be aware of that. So we are going to have normal force is going to be a positive value. We're going to be adding, now once again, Fg is going to be going down. So Fg is going to be a negative value. And now we need to be thinking about F applied on the Y. So with force applied on the Y, think carefully where it's going. Note the arrow on your free body diagram. Your force applied on the Y is going up. We chose up to be positive to give our normal force a positive value. So that means your force applied on the Y is going to be positive. So I'm going to switch colors here to emphasize some significance. I'm going to circle this and I'm going to put an arrow and a star. Ladies and gentlemen, the reason why I did that is because this is the most common mistake I see on this topic, is forgetting force applied on the Y, or FAPI, as my last year's Physics 20 class called it. So be careful, okay? Be very, very aware of that. Okay, we're going to go back to red over here. Okay. So F net on the y is going to be 0 newtons because we're neither accelerating up or down. I can then move these guys over to get my value of Fn. This is negative, so I'm going to add Fg. This is positive, so I'm going to subtract force applied on the y. So I'm going to rewrite this equation. My normal force, ladies and gentlemen, is going to equal to Fg minus my force applied on the y. Okay, so be aware of that. Watch how we did that. Look how we did that. Maybe watch that piece a couple times so that way you get that force applied y there. Now, Fg, ladies and gentlemen, is equal to mg. Okay, there we are. I am now going to solve for my Fn. I'm just going to scroll down a little bit here. Okay. Now, we know the mass of this object from earlier in the question. We're just going to double check. It is 12.7 kilograms. Okay. G is always the same, of 9.81. And we're going to subtract our FAP, force applied on the y, this guy here. Your all digits, ladies and gentlemen, every single one of those digits you got in your calculator is going to be our 40.1478 ... And we're going to get a value of our normal force to be the lovely value of 84.43916 ... newtons. Okay, so ladies and gentlemen, we have our normal force, we have our force applied on the x, and we have our mass. We can now finally find our acceleration. Okay, so ladies and gentlemen, we're trying to find acceleration. I'm going to divide out that mass. Okay, and now I'm going to put my values in. So my force applied on the x is my 44.5886 ... which you are going to use all of your values in, ladies and gentlemen. We're going to subtract this from mu Fn. Mu, ladies and gentlemen, from given to you in the question is 0.23. And the normal force, which we calculated right here, is our 84.439 ... Okay, I am then going to divide the whole lot by my mass, which is 12.7 kilograms. And very carefully making sure everything goes properly into my calculator, we're going to wind up with an acceleration of 1.9817 ... meters per second squared. Okay, I want sig digs, units, direction. All right, this is a vector, and I did not ask for just magnitude. So I want a total of 3 sig digs, and we're going to put 1.98 meters per second squared. And our direction, ladies and gentlemen, is east from the direction that we were traveling in earlier. Whew. What do you think? Pretty awesome, hey? Love that question. So there's a lot involved with it, so pay close attention when you're doing these. Watch out for that in your assignment. All right. So we're going to scroll down a bit here, and I want to, do some practice problems. Give this a try before you do your assignment. And I want to bring to your attention before we go some of these scenarios where you have your force applied acting at a downward angle here. Your concept is going to be the same. However, the biggest difference with these guys, ladies and gentlemen, is when we're going to be making our F net equation on the y. So I just want to build this equation with you here for these cases where we are working on a downward angle, and because the last two questions were upward angle. Okay, so on the y, we have, same as for F net y, we have our normal force acting on the object. We have our Fg. But notice, ladies and gentlemen, on your diagram, our force applied on the y is going down. So that's going to change how we set things up. So we still have our normal force. Okay. We are now going to be having Fg acting on the object, which is down, so it's negative. And force applied on the y is down, so it is -2. Okay, I just got to erase this so I can fit that there. Okay, so force net on the y is going to be 0 newtons because we're neither accelerating up nor accelerating down. And then I'm going to add over Fg, and I'm going to add over force applied on the y. So that means once I finish with this equation, I am going to have my normal force is going to equal my Fg plus my force applied on the y. Now, the reason why this makes sense is because when you're pushing down on an object, you not only have gravity, which is going to be putting pressure on the floor on that object, you are now pushing on it too. So, and the downward force applied on the y is going to increase that normal force. So that means when you're pushing down on an object, you're going to have increased force of friction. So, which makes sense. You guys have all pushed stuff around or stuff before. And if you're pushing things around and you're pushing down on it, it's going to drag and it's going to be a lot harder to move. Whereas if you're going to be moving something and if you pick it up a little bit and apply an upward force on the y, it's going to reduce your normal force, which is therefore going to reduce your force of friction. Okay, so I hope you guys enjoyed that video, ladies and gentlemen. Do some of the practice problems on the screen. If you haven't already done so, watch the field trip, or I will be pushing around my desk chair. All right, so have a good day, guys, and no fires, injuries, or explosions.